that a start? Hello, my dear students, and welcome to a video help session for exercise 3.4. Here, we're combining some material from earlier in the course where we talked about composition of compounds and structures and analyzing the composition of compounds with mole ratios and the mole concept. So, and a little bit of reactions, because in the early days of chemistry, a big part of the research was determining the structure of molecules, and before that, because structure determines function, but before that, it was determining the composition of structures. And when you do a destructive analysis of certain compounds and break them down into elements, certain elements you can combine in different ways to measure relatively easily. For example, carbon, you can convert to carbon dioxide and capture that very easily. Hydrogen, you can combine with oxygen to form water, and oxygen you can combine with hydrogen to form water. Nitrogen, you can do simple experiments to make various nitrogen compounds that you can capture and measure, not as easily as you can, for example, CO2 or water, but doable, especially with modern chemistry. So this exercise 3.4 takes us through 4 chemical compounds with relatively complex structures, certainly more complex than some of the ones we've been learning about earlier. They're all organic compounds, and asks you, what would I expect if I did a combustion analysis of this compound? And the first one in question 1 is styrene. And I give you its structure. And you need to know how to look at and read and interpret a molecular structure. The dark black balls in that structure, a structure, for example, like this fatty acid, the black balls would be carbon, the white or pale yellow, because this is an older model, most of the time we use white, I've seen pale blue used too, are hydrogen. Oxygen is red by convention, and nitrogen is blue. Well, on this one, if you count up the black atoms and the white atoms, you'll see that there are 8 carbons and 8 hydrogens in styrene. So this is exercise 3.4, and question number 1 asks for the combustion analysis of styrene, the monomer precursor to polystyrene, or what we make foam ice chest or foam archery targets out of. And this has 8 carbons, if you add them up, and 8 hydrogens. Its formula is C8H8. Or you can Google it or look it up, and or if you're in a laboratory and you can go over and reach for what we call a CRC, Chemical Rubber Company is the publisher, Handbook of Chemistry and Physics, you can look up formulas for all kinds of compounds there too. And what this means is when I burn this styrene and capture the hydrogen and the carbon, I'm going to have 8 carbons in styrene, and therefore I'm going to have 8 CO2 produced. And I have 8 hydrogen, and therefore when I combine this in oxygen, oxygen's free, The atmosphere has 20%. I don't necessarily have to use pure oxygen. But when I convert this hydrogen to a product I can measure, water, and it's easy to trap water, many hygroscopic compounds, are available that latch on to the water and change their mass that is immeasurable. Because there's 2 hydrogens in water, I'm going to make 4 H2O. So 4 H2O are produced. So let's read the question. How many moles of carbon dioxide and water, H2O, will be produced by combustion analysis of, and this varies from college to college. This varies from class to class, and even within a class, if I have a big class, from person to person. But let's take the example I have in front of me, and that is 0.025 mole of styrene. And so, this says for every mole of styrene I'm going to produce 8 moles of CO2. And for every mole of styrene I'm going to produce 4 moles of water. Okay? So, if I want to do mole ratios and do it the long way, this means 1 mole of styrene, C8H8, produces 8 mole of carbon dioxide. And the question is, how many moles of carbon dioxide will be produced if I have 0.025 mole? So the proper way to do this, setting up mole ratios, as I'll show you in the second part of this video, is to cross multiply and solve for x. So 1x equals, and if you look, our moles of CO2 will cancel out, and our moles of styrene will cancel out when we cross multiply here. And so 1x will equal to 8 times 0.025, which means x is equal to, or our moles of carbon dioxide that much will produce will be 0.02 mole CO2. That's it. That's your answer. Okay? That's one way to do it. The other way, now there's another way. Let me show you the way some of you are going to quickly go to the end. This is the official way to do it. Set up your mole ratios and solve for your unknown. But if for every mole of styrene I get 8 moles of CO2 produced, all I need to do is multiply that by 8. 0.025 times 8 is 0.02. So for the water produced, I get 1 mole of styrene per 4 moles of water. Now I'm going to multiply the 0.025 by 4, which is what? It's going to be 4 times 0.025, and that's 0.01 mole of CO2. I've also known students who think this way. Well, I'll solve this one. 8 moles of CO2 produced for every mole of styrene means that if I have 0.025 moles of styrene, I'll make 0.02. I make half as much water, I just take half as much of that, 0.02 to 0.01. And those are your answers. So, in this help session, I'm literally solving your problems. Let me go on. Notice, we didn't need to do molecular weight, we didn't need to do molar mass. So let's go on to the second problem. When we download this, I'm sorry I don't have a smart board. I actually have it pulled up right here. I was going to work it on the board. but I'll do it off to the side. This one's a little harder because it asks you for more information in your elemental analysis, but the next one is a analysis of 0.02 mole of aniline. By the way, aniline is a starting point for many dyes and pigments, and a common chemical found in the organic chemistry labs. If you count this up, you notice it has a blue atom here, that's nitrogen. And so one aniline molecule has 6 carbons. It has 7 hydrogens, and it has 1 nitrogen. And its formula is C6H7N. And there's its structure. Okay? So what does this mean? That means every mole of aniline will produce 6 mole of carbon dioxide. And every mole of aniline will produce, because it's H2O, will produce 3.5 moles of water. And what we're going to capture and measure is nitrogen gas. So it's going to produce 0.5. 1 mole of nitrogen is going to produce half a mole of molecular nitrogen. The normal form of nitrogen. Every breath you take, our environment, our atmosphere is 79%, almost 80% nitrogen, okay, 20% oxygen. And it's present as N2, triple bonded ends together. So, I have 0.028 moles. Did you see how to do it? I'm not going to set up mole ratios. 1 mole of aniline gives 6 moles of CO2, so 0.280 moles of aniline should give X moles of CO2. I just know that in the end, I need to multiply it. If I had 1 here, I would know what I had. If I had a half a mole, 0.5, I know I would change that to a 3. So let's just do that. 6 times 0.0280 is going to give me, and let's have the math already done, 0.168 mole of carbon dioxide produced. And here, 3.5 times 0.0280. So this is 3.5 mole of H2O multiplied by 0.0280 mole of aniline, per mole of H2O. And, this is 3.5 moles of H2O per mole of aniline. This is 0.028 moles of aniline. The anilines cancel, and what I'm left with is moles of H2O. So if you multiply 0.0280 by 3.5, you get 0.098 mole of H2O. And for this one, I just need to multiply it by 0.5, or divide this number by 2, cut it in half. So that would be half of 280, make it look like a 0, would be 0.014 mole. Actually, 140 if we want to keep our significant figures, mole of N2. It's the answer to your second one, okay? So, let's do the other 2. I'm going to do them quickly and get through this one. So, the next one is aspartame. You may have heard of aspartame. It's technically asp-phenol methyl ester. It's a short modified dipeptide that is intensely sweet when you put it into the body. We don't like to put chemicals into the body if we can avoid it, but this one is probably better for you than sugar. It's the artificial sweetener in equal. Those are the blue packets. So this aspartame, and this is number 3, this aspartame has the structure. If you count that complex structure up, or you look it up, you will see it C14, H18, N2O5. And we want to know how much CO2, H2O, and N2 is produced by the complete combustion of the aspartame molecule, given the fact that I don't have a mole. We know that we'll make 14 moles of carbon, CO2, excuse me, and we'll make 9 moles of water. We'll make 1 mole of nitrogen for every mole of aspartame. Oxygen is a little bit harder to analyze, so we're not going to determine that in our rudimentary combustion analysis. So I said I have 0.0137 mole, and by the way, these questions are straight from the Chem Libre assignments for the reading that matches this module. All I've done is change this quantity. But if I want to do this quantity, all I need to do is multiply it by 14 for the CO2, by 9 for the H2O, and by 1 for the nitrogen that will be produced by its complete analysis. So let's do it. 0.0137 mole of aspartame multiplied by 14 mole of CO2, oops, big O, CO2 per mole of aspartame, per 1 mole. Okay, so my moles of aspartame cancel, I'm left with moles of CO2. 0.0137 times 14 just happens to be 0.192 mole of carbon dioxide will be produced. There's 1/3 of your correct answer. And then I take 0.0137 mole aspartame times 9 mole of water per mole of aspartame, and I would end up with 0.123 mole, 123, of water. And you don't really have to do the math, but since it's 1 for 1, whatever this value is, it's going to be my value for nitrogen, because 0.0137 moles of nitrogen per mole of aspartame, moles of aspartame times 1 mole of nitrogen per mole of aspartame gives me 1 times 0.137, so 0.0137 mole nitrogen gas. We'll zoom in on those answers and move on to the next one. This next structure is very complex. If you look carefully, there is a S, and you can capture sulfur atoms very easily, turning them to sulfur dioxide, then dissolving that in water and combining with water to form sulfuric acid, or it's actually a component of sulfur dioxide. It's a component of, well, it's an atmospheric pollutant that produces a component of acid rain. It's also sometimes the smell of Pine Bluff. I'm here in Pine Bluff, and thanks to the paper plant, this is something we live with. Penicillin G is more correctly named benzyl penicillin, as opposed to penicillin G, the one you take when you get penicillin pills. When you go to the doctor's office with strep throat, this is the one they inject you with. You cannot eat this one because the benzyl attachment in the penicillin is sensitive to the acids in your stomach. So you need to take a more modified version of penicillin that can make it through the stomach and be absorbed by the small intestine and reach a therapeutic dose. But when you get an injection, a penicillin shot, this is what you get, benzyl penicillin. So benzyl penicillin, Pen-G is Pen-G. Okay, you get a different one. Oh, you get Pen-VK. I'm sorry, it's Pen-VK. So penicillin, one N and two L's. A lot of people spell it wrong. So penicillin. Should keep my lowercase and capitals consistent. So penicillin, also known as penicillin G, as opposed to pen. They usually add an extra N sometimes when they write it out this way. VK, that's the one you take in the pills. Anyway, it has the structure C16. Yes, you can go down there and count them, or you can look it up. H18, N2, O4S, and we need to solve 4 problems, and I said that you are given 0.0590 moles. 0.0590 mole of penicillin. Okay? So, if I want to know how much CO2 I produce, there's 16 carbons. So, 16 times 0.0590 is equal to 0.944 mole carbon dioxide produced by the complete combustion of 0.0590 moles of penicillin G. Okay, so the next one is water. There's 18 hydrogens, but that only gives me 9 waters. So 9 times 0.0590 is equal to 0.531 mole of H2O is produced. For the nitrogen, there's 2 nitrogen, so it's 1 for 1 again. It's 1 times 0.0590 is equal to 0.0590 mole of molecular nitrogen, or N2 gas. You're breathing it in right now as we talk. And finally, the sulfur, to make SO2, sulfur dioxide, you produce one of those too. So it's the same answer, the same numerical value for the different answer of 0.0590 mole of sulfur dioxide produced. Sulfur compound smell. So I will work the second half of this assignment in a separate video help session. It's going to be important because I won't give you these kinds of complex questions on a test, because the tests I've given you, though they're online, open book, and open reference material, you have to have a calculator and you have to have a periodic table and everything else. The next set